Hey everybody, welcome back. Last time we talked about polarization and we talked about how that is one example of light that requires that we have this electromagnetic wave moving through, and then we can't just think of it as a light ray. But as I mentioned, we're going to start transitioning over into this approximation called geometric optics, where we do treat it as a light ray. But even then, we're going to be talking about basically how this wave front is propagating, and we're going to use that ray to just represent the direction of propagation. So it's still going to be this electromagnetic wave. But today we're going to talk about what exactly is it that's propagating. And we're going to find that the fact that it is a wave and the way at which it's propagating through space at a very deep level has some kind of surprising effects on this wave. It allows it to bend in ways that you might not expect. So this is going to be somewhat of a conceptual lesson here. There's not going to be a lot of math here that we're going to be working with. Instead, we're going to have to understand kind of the deep physics of what's going on with it. So hopefully we'll have some fun with it. Let's get started. Okay, so before we get too far into it, let's kind of review what we know about waves in general. And let's get my pen here. So let's imagine that let's say we're plotting the electric field. Remember that the magnetic field is going to be here as well, but it's going to be at a 90-degree angle. And well, I really don't want to draw in 3D if I can help it. So that last wave is a little flimsy. There we go. So if I'm plotting the electric field, and I can be plotting it in both space and time, then the distance in space from here to here is the wavelength. And we use that Greek letter lambda, lowercase letter lambda, to represent the wavelength. And a lot of my students call it chicken foot because it looks like a chicken foot. You can call it whatever you want. Remember, it's just a symbol. But we generally use that symbol to represent the length of the wave. And that's always the distance from one peak to the next. And I'm going to do this in red because it's not true. This is not the wavelength from the peak to the trough here. That's going to only be half a wavelength. So similarly, if we go ahead and get rid of the red, so that's bad. Similarly, you've got to be really careful about measuring your wavelength from the zero here, because from here to here is also half a wavelength. So even though they're both at zero, instead you have to say, okay, I'm at zero and I'm increasing. So my derivative is positive. And now I'm back at zero and I'm increasing. So my derivative is positive. Here I'm at zero, but my derivative is negative. So I'm only going to be at half a wavelength there. So I can measure it from here to here, and I'm going to get the same value. And hopefully you see that I could also go from trough to trough, and I would still get the same value. All of those are the wavelengths. They're not going to change. For me, I generally am just going to do it from the peaks because I find that's the most easy thing to think about. That's where the energy is where all these peaks are. But you should keep in mind where you can define it. But it is not from here to here, nor is it from here to here. All right. Let's get rid of some of my lines there. So we're back to our wavelength. There. Okay. The other thing that we talked about was the frequency, which we used F. And we said that the frequency was the number of peaks per second. So, imagine that this is my eye, and every time one of these peaks hits my eye, a tone sounds. So it goes beep, 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 beep. Well, if I've got another wave here, maybe that has that longer wavelength like we did before. So this has a much longer wavelength. If these waves are traveling at the same speed, and only if they're traveling at the same speed, then I'm going to get more peaks per second in the top wave than I am in the bottom wave. Now, remember, if they weren't traveling at the same speed, it would be possible for the bottom wave to actually be earlier if it was just really cooking along and coming in. But we know that all light travels at the same speed, which we use the letter C just because that was the constant of integration from Maxwell's work. But that has a value that's fixed by the constants of the universe. And it's 1 over mu 0 times epsilon naught. And this, remember, is the strength of the magnetic field, and this is the strength of the electric field. And it makes sense that they would both be there, right? Because light is an electromagnetic wave. It has to have both functions in there. Okay, so we've talked about the wave speed, we've talked about the wavelength and the frequency, and then we said, okay, there is a relationship between them. The frequency is inversely proportional to the wavelength. And you can see that from the graph that we have here. The more peaks per second I have, the higher the frequency, the shorter that wavelength is going to end up being. So that's a very useful result. We've also talked about the energy. And we said, okay, well, the energy, and again, here, this is not the electric field. It is not a vector. This is just the energy. Unfortunately, again, we're out of symbols, so make sure you keep up with us. That is going to be directly proportional to the frequency. And if you think about it, if I have a wave that looks like this, if my electric field looks like this, where it's always zero, I don't have any frequency, I don't have any energy at all. On the other hand, if I had one that was up here, so maybe this was my energy, and again, here I'm using E to be the energy, then okay, now I've got a lot of energy. So you could think about the more of these peaks, which contain the maximum energy that hit my eye, the more energy is going to be contained in that wave. And so it's going to have to be directly proportional to the frequency. And then the constant of proportionality is Planck's constant, which comes out of quantum mechanics, and that's 6.626 times 10 to the minus 34. And then to get my units to work out, it's got to be joules per hertz. And that's a tiny, tiny number. And that comes about, because of quantum mechanics, which we probably won't get into in this particular course. Okay, the other things that we've talked about then is we've talked about the amplitude. And the amplitude is, you can think of that as being the height of the wave. It's the strength of the wave. If it were sound, it would be volume. If it's light, it's the intensity. So the higher the amplitude, in the case of light, the brighter it's going to be. So if I have two waves, let's go ahead and get rid of this bottom wave for just a second. And let's suppose that my two waves have identical wavelengths and therefore identical frequencies. But this bottom one comes up like this. So you see that, as best I can draw, their wavelengths are the same. The distance between the peaks is going to be the same. However, this one goes up to a much higher amplitude than the top one does. So that's an important thing. And we're going to be working with amplitude when it comes in here. So the last thing we want to talk about here then is the phase of the wave. Now, we've drawn these two waves to be in phase. Let's take two waves that have the same amplitude, just to kind of deal with just one quantity at a time. We don't want to mix quantities if we can help it while we're learning. So I'm going to try to draw a wave here that has the same frequency, the same wavelength, of course, and the same wave and the same amplitude. But I'm going to draw it 90 degrees out of phase. And so what that means is that when this one is positive, this one is going to be the opposite. So if it's 90 degrees, when this one's positive, this one's going to be zero. I'm going to have to redraw that so I can get that to come straight down. I want them to line up. Let's see if we can do that. So right here. So this one's positive and we want that one to be zero. When this one is zero, we want it to be at its negative. When this one's negative, then we're going to be back at our zero. And then here, as I'm increasing, I'm going to be at the positive for this wave. By the time I get up to here, to this one, which I'm kind of losing my alignment here, it's going to be negative. So my wave then is going to look like this, as best as I can draw it. And then if I were to continue, let's say this wave goes up at zero, when that one is at zero, then this one must be up here. Okay, and I'm not going to try to draw the rest of the peaks, but hopefully you can see that these waves then are what we call 90 degrees out of phase. And so if I were going to draw them superimposed on top of each other, it would look something like this. Okay, not quite like that, but anyway, trying to draw these at the same time is difficult. Anyway, hopefully you can see how those are lining up. Now, if I'm 180 degrees out of phase, though, let's watch what happens. Oops. Get my eraser back. Okay, so now I'm going to try to draw it 180 degrees. And all that means is when this one's positive, this one's going to be negative. Their zeros are going to be in the same spot. And then when this one's negative, the top one's negative, the bottom one's going to be positive. And so that's a little bit easier to draw, like so. All right, well, If I have these two waves together, then the electric field is a vector. So remember, the electric field is a vector, so I can add those vectors. Here, my electric field is positive. Here, my electric field is negative. So when I add them up, what am I going to get? It's going to be 0. The electric field is going to be 0. And this is, if there's no magic here, it's simply because my electric field is a vector. Same thing here. It's negative, but here it's positive. And so you see that that's going to hold true actually everywhere on the wave. So when I combine these, the electric field is actually completely gone. And so this is something we're going to talk about next time called interference. And this is destructive interference. The wave is just gone. Now, this wave then is propagating and it can combine with other waves. Let's suppose that I have two waves that are in phase. So they're completely in phase and they're the same amplitude, same frequency, same wavelength, everything. So it's basically like this. Now they're vectors, remember, so I'm going to add those vectors, and what do I get? Well, the amplitude is going to be twice as high, like that. So they're still interfering, but we're getting more energy out of that, and we're going to learn that we're going to call that constructive interference. The bottom line here is that that's going to be brighter. So all of these waves can interact, and this is not just light. Yes, light would be brighter, sound would be louder if I were able to bring this together. There's all kinds of waves out there, sound, light, but also water. So let's clear this out and let's take a look at some water waves that are coming in. And we want to see if we can figure out on a deep level what's going on here. All right, so let's slide my picture over, and this is in your book. And so it's a little hard to see in the picture, but out here, before the surf breaks, the wave fronts are completely parallel to each other. So if I were going to draw them as they come in, they would be, if I'm just going to draw the tops of the peaks, then it would look like this. Now I want you to visualize what's happening. So it comes up to the first black line, then in between the black lines, it's negative. And then it comes back up again to the second black line, and that's going to be the top of the peak. In between that and the next black line, it's negative, and then finally it comes back up again and comes back negative. And this would continue as the wave propagates across. All right, so what we're mapping here, if I'm going to draw this from the side, I'm going to try to draw this from the side. This is my electric field, and it's going to be at a maximum here, then a minimum, then a maximum, then a minimum, then a maximum. So each one of these peaks lines up with a wavefront. That's what we're trying to show. So what I'm trying to do is come up with a shorthand way of being able to draw these wavefronts without having to draw these squiggles, and so that we can see as it propagates through space. All right, so as this water wave approaches, and that's, again, a water wave is still a wave. It's these water molecules going up and down. As the water wave approaches, then all of these wavefronts are going to be parallel. But then notice what happens. As soon as it hits the surf break here, as soon as it hits these breaks, all of a sudden the wavefronts become curved as they move towards the shore. The same thing is happening over here. Something is happening just because it hits that break there that's causing the wave to bend. And there's no obvious reason why it would do that. And if you think about it, if I have, let's say this is one surf break and this is the other. We'll color those dark so we see. So this surf break would be this one and this surf break would be this one. You would think simply that the wavefront would simply continue straight through, just like that. But in fact, it doesn't. And in fact, it's going to end up curling this way. Oops, lost my pen. And this way, moving off at this angle, these spherical wavefronts moving through. So there's nothing in the idea of a wave that would make us think that it would do that. So let's see if we can figure out what's going on. And let me get my eraser here. Let's just go and erase this thing. All right, so take a look at this diagram here. There is a way that we can draw this idea of spherical wavelets. And so if you think about each particle of water right here, so we've got a bunch of particles of water in my wave. Those particles of water don't actually move forward, maybe a little, but not much. And what they're actually doing is they're simply moving up and down. But as this particle moves up, it drags the one next to it up a little bit slower. And you've probably seen that if you've ever played with things in the water. You can have something floating here and you can drag up beside it, and it'll actually drag that submerged object up a little bit. Then as it comes down, it drags this down. So if I start out with perfectly flat ocean and I get a wave for some reason, it's caused by the wind usually, and I get a wave here, that's going to drag that up, but it's going to be behind it. And by the time before this one can get to the top, this one will have started back down. So the wave particles are just bouncing up and down and up and down. But each particle is causing the particle next to it to move. See if you can think about that. It's because it's dragging, because these particles are dragging. So what we can do, a good approximation to this, is to consider each one to be dragging everything around in a circle, all the ones around it. Because if you think about it, it's going to be acting all the way around the water that it's dragging. It's not just going to be if this particle is moving up and down, it's not just going to drag the one right up in front of it. It's going to be kind of in a sphere around it. So it's going to be a spherical wavelet, we call it, these little pieces that are coming out. Okay. Now, as you can see here I've focused on it. As these come together, the wave from this one, the wavelet from this one, and the wavelet from this one combine. And so right here at this wavefront, they've actually reinforced each other because they're in phase. Now, I haven't drawn all of them, and so it looks like there's a gap here. But remember that there's also there's a wavelet here, and there's a wavelet here, and a wavelet here, and a wavelet here. So if I put all of these together, then what I get is the next wavefront. And this is why it seems to propagate forward, even though it's a sphere. And that's important. It's a sphere that the wave particle, the water particle, is dragging around. But because those spheres interfere constructively, then they reinforce each other in this nice straight line. And so the wavefront seems to just propagate straight forward like this, even though the particles themselves are dragging everything out in this circle, in this sphere around it. Right? Take a minute and pause the video and kind of sketch with that. See if that makes sense, because that's going to be critical for what we're going to be talking about here in just a second. So this model, we can use the reality of this to actually help us figure out what's going on with other kinds of waves. So water waves work because of this water molecule that's moving up and down. Sound waves, though, what's propagating in sound, do you know? What's actually the air? It's air molecules. And so it works exactly the same way. If when you speak, you take air into your lungs, and then when you breathe out, your vocal cords vibrate the air molecules, but they only vibrate the air molecules in your throat. Those molecules then drag the molecules right next to it, which drag the molecules next to it, which will do the ones next to it, and so on and so on. There's nothing physically coming out of your mouth and into somebody else's ear, for which we're kind of grateful. But the idea of what's going on, though, is that these particles, as this one moves, it drags the one right next to it, because air is simply a fluid. And if you are an engineer and you're taking fluid mechanics, you're going to realize that there's no difference between air and water. It's just different viscosities of fluids with that. Okay, so air works the same way. So we chose a time of 1 second to plot this, as you can see here. But there were many of them, but they reinforce each other no matter how many there are in between. There's, if it's, depending on the speed of the wave there, it doesn't matter. They will only reinforce each other at their peaks. And so that's very useful. So for light, or for sound, that might be around a meter. The typical wavelength of sound is around a meter or two, somewhere in there. Whereas for light, it's about 500 billionths of a meter, 500 nanometers across. So they're still waves, though, and they're behaving the same way. But it makes you wonder, what about it with light, with electromagnetic waves, is actually propagating? I mean, if you think about it, that's a little weird, right? So we've got this. Let's go back to what we were thinking about with electric charge. Move this over to the side for just a minute. So I have a positive charge here, and by itself, there's no force, right? I have to have some other charge. And here, if it's negative, then they're going to be attracted to each other. But we know that the electric field exists even without another molecule there. That's what Maxwell's equations are telling us. Maxwell's equation says that the electric field diverges positively from a positive charge. And so it looks like this. Now, if I magically get another charge here, we can see how it's going to interact by seeing how it moves along this field line. But what's making it move? In the case of the waterways, we've got something pulling. Normally, when we think about forces, we think about contact forces. So you're grabbing something and you're pulling it. It's conservation of momentum. We've dealt with conservation of momentum all last semester, and that makes sense. What about this is actually pulling? It's not this force from Star Wars, right? It's not some spooky action where you can sit there and go, woo, and you can pull this in. It doesn't work that way. So, and yet it appears to be that way. It appears that there's this field everywhere. Well, what's happening, and this is going to get into quantum mechanics, that is not for this course, but it's just to give you an idea. What happens is that this particle, this charged particle, emits a cloud of interaction particles that it can use to interact. And so it interacts, it sends out this big cloud, massive cloud of these particles. These are supposed to be circles, but I'm in a hurry, right? And so they're all there. And of course, the further out I get, right, because they're propagating outward from this central charge, the further out I get, the farther they're going to be spread out, which means if I have some other particles, interaction particles, so let's say I've got my charged particle here, my negative one, right, in which case they're coming this way. Let's keep it simple. Attraction's a little harder than repulsion. Let's say I've got another positive one, so I've got my field going like this. Let's do it that way, right? So it's also putting these out. And if I think of these as like billiard balls, pool balls, eventually these particles are going to collide. So this particle that this charge put out is going to collide with this particle that this charge put out. When that happens, they're going to move away from each other. And so that force then gets transferred to the next one, to the next one, to the next one, which then pushes the charge away. And that's actually what's causing the repulsion, is the charge is emitting this cloud of interaction particles. And we call those interaction particles, in the case of electromagnetism, we call them photons. So this, and again, it's quantum mechanics, but this is literally what's happening with that electromagnetic wave, is that the photons are what's moving through. And one photon disturbs the next, and so that's how the field propagates. And because of the speed of these photons is going to be the speed of light, which we decided was this, because at a fundamental level, it depends upon the charge producer that's making it. The strength of it is determined by those two constants. So those photons are also moving at the speed of light, and this is why the electromagnetic disturbance propagates at the speed of light. But the principle there, though, is that it works exactly the same as the water waves. Let's go ahead and show that. Instead of showing in all space, we're just going to show it in one direction, like we were doing. So here, let's look at, so I've got some charged particle over here that's oscillating. And it's off the screen, it's off the stage where we can't see it. But that's giving me a photon here that's oscillating. When it interacts with another photon in the cloud, then it's going to start oscillating. And so that's going to get carried on through. So it sends out this interaction through here exactly like the water wave. And so I end up with these wave fronts that then propagate through. So what we've shown here is that light operates exactly like a sound wave or a water wave, and for the same reason. You have these interaction particles, and that's what's dragging everything, and that's what's making it propagate. And it's also why light doesn't travel instantaneously. that changes in an electromagnetic field cannot happen instantaneously because I've got a particle here and I've got a particle here. They can't drag this one at the same time. Right? Side note, some of you have heard of quantum entanglement. Okay, yes, that's a thing. And that's what Einstein actually called spooky action at a distance. And he didn't really understand it, even though he got his Nobel Prize for quantum mechanics. And he didn't like it because that does not require any kind of propagation. And that's another matter entirely. That actually does happen instantaneously. And so that's the secret to quantum computing and why it's so fast. With these photons, they're limited to traveling at the speed of light. However, if two particles are entangled, any change I make over here happens in this one instantly because it doesn't have to use those interaction particles in between these photons to transfer the force. And for every force that we have, there is a particle that's causing that to be exchanged. For gravity, we call it the graviton, things like that. So these particles are real, but they allow us to explain how this propagates. But because they are particles that propagate in the same way that a wave does, then we can say that light is also a wave. And so both interpretations apply at the same time. And we'll be looking at that in detail towards the end of the course here. Okay, so all of that was to convince you of the next part. Let's go to the last page of this section then. Let's just go ahead and delete this and we'll move this over. Okay. So now we've got a similar case to what we had in our picture with the seawalls, with the surf breaks coming in. So here I have my wavelets. It could be water, it could be light, it could be sound. Doesn't matter. But I've got an aperture right here. A slit, sometimes it's called. Aperture is the technical word for it, but it's a hole. It's a hole in it. So what we want you to do, pause the video and draw those spherical wavelets as they propagate out from this wave emitter right here. Draw what they're going to look like, and then draw the next wavefront and see what you get. Go ahead and pause the video and do that now. It's real important that you go through this exercise. Did you get done? Pause the video if not. Okay, so this is emitting those spherical waves. And remember, when I say that, I mean that's that interaction particle that's acting around it. In this case, if it's water, it's literal particles dragging each other. So they combine then up here. Now, these wavelets right here combine, but they can't get past that right there. Now let's look at this one here. These two wavelets that I have here. Here in the middle, they're combining. But is there anything up here and up here to combine with, to reinforce? When I was behind the wave, behind the surf break, there was, right? No matter where I was here, I had something up here that could interact with it to keep it going straight. So no, there's not. So the wavefront that emerges then looks like this, because there's nothing to flatten it out up here. There's nothing for it to interact with up on the top up here. And then the same thing is happening down at the bottom. I get one that looks like this. So the end result then is that it seems like, and again, we're going to start drawing our rays that we talked about before, these geometric optic rays. We're just showing the path of propagation. So when it came in, the wavefront's propagated here. And I draw that so that it's perpendicular to my wavefront. That's the way I want it to be. And so then this is going to be perpendicular to this wavefront. And so what happens is that I have these spherical waves that are emitted outward. And that's what's causing the pattern that you see in the picture with the water waves from that. So go back and take a look at that picture. I'm not going to bring it up here. I want you to think about it. Go back and take a look at that picture. And how many apertures must there actually be? We only see one in the picture. But take a look at the waves very carefully. How many apertures are there? Pause the video. Go back and take a look. There actually must be 2 of them there. And if you don't believe me, go back and see how those waves are being curved. And there is actually another aperture just off the screen that you can't see from there. So as sound then, this is why you can hear sound around a corner. So let's say that, let's get rid of some of our from our drawings here so that we can see what's going on. And we're just going to draw the ray line, so the line that's perpendicular to the wavefronts, that's perpendicular to the wavefront coming through here. So let's say that I've got a sound wave that's coming right here, right? If you were standing over here and that sound wave were a ray that just kept going straight through, it would never reach your ears. You would never hear it. But we now see that what's happening, though, is because of these spherical wavelets, the sound bends this way and this way. And that's why, even though the sound, the person talking maybe, was over here, you can hear it around the corner. And this effect is called diffraction. So the wave diffracts around that corner there. So as soon as the wave hits an aperture, and that could be a doorway, it could be a hallway, it could be a window, it could be anything, then because these wavelets are being blocked from reinforcing this to keep it going straight, well then, since it's a sphere, it's going to follow that sphere and it's going to bend. And I'm going to get that pattern. We're going to be using this very extensively for a long time, for most of the semester here. So make sure that you understand how that works. All right. Now, suppose, let's look at this next one. Suppose the aperture is very large compared to the wave. So let's suppose, again, that I've got some sort of either the wavelength is very small or the aperture is very big to that. So let's take a minute, pause, draw in our wave emitters, and let's see what's going to happen with the wave. How is it going to propagate? Pause the video and take a look. You got it? Okay, so my wave is coming in this way, right? And now I've got these spherical wave emitters that are going to look like this. And so they're going to reinforce here. But as soon as they get to the aperture, right? Now, most of the wave is actually still going to be straight. But there will be a little bit that bends around the corner. But compared to the entire wavefront here, that's actually going to be a very small part. So most of the wave is still going to be propagating this way. But there's a tiny little bit maybe that's going this way. Because if you think about it, if I have, making this up, 100 wave emitters here, only these ones on the end are not going to be canceled out from that. So only a little bit of the light comes through. This is what's happening with light. And this is why you can't see around corners. Because the wavelength of light is very small compared to any aperture that you might run into. A typical doorway is about 1 meter or so from that. Well, sound has a wavelength of about 1 meter, and so it diffracts around it very easily. Light actually does diffract around the corner. You actually can see around the corner, but it doesn't diffract much, and it's not enough that you can perceive it. However, if we have very, very, very tiny apertures, then we can actually see this wave bend from here. And the classic example of that is a CD. So like a CD-ROM or an audio CD. The way this works is there's grooves in that CD that are made up of the little bits that are burned into it that encode the sound from there. The spacing in these grooves is less than a micron, about 1/1,000,000th of a meter from there. Well, that's very small, right? And even though light is on the nanometer range, which is about 10 to the minus 9, a micron is about 10 to the minus 6. And so that's close enough that if I shine light either through it or reflect off of it, then I'm going to be able to see that bending of the light from there. Another way that you can do this, if you have like an umbrella that has threads in the umbrella that are very, very close together, if the weave of it is close together, you can actually see this. And say I get a big bright light, we'll color it nice and yellow here. Say I get a nice bright light through here, I will actually see that bending waves. I'll see that diffraction pattern, it's called, through there, because the separation between those threads is so very small if it's a very tight weave then I can conceivably actually see the diffraction. But for normal everyday life, you're not going to be able to see around the corners because we've got a distance of 1 meter here, but the wavelength is on the order of a few hundred nanometers from there. And it's just not bending enough. There's not enough light there that gets bent for you to be able to see it. All right, so take a look in your book under interference. This is microtask 1. And we want to start to get an idea of what pattern is going to be produced. So now we have not just one slit, one aperture, but 2. And so let's see what kind of pattern that we can get with this. Let me switch to my pen. So what we want you to do, each of these dashed lines that you see here, let's use a different color. Each of these dashed lines that you see here, I've drawn that to represent where I will get the 2 spherical waves are going to be in phase. Now, let's make sure that we're all understanding what we mean by that. So this wavefront, this top wavefront, is being produced by this aperture right here. And then I have another one that's extending out here. But notice that it extends out in all directions. So if I have one, the one on the bottom is looking like this. And then we use a different color here. The one on the top is looking like this. And this is very similar to what we did when we were talking about the wavelets that were on the line here, except now they're being produced by 2 separate apertures from this. So wherever these 2 combine constructively, they're in phase, and so it's going to be bright. If they combine destructively, 180 degrees out of phase, then they're going to be dark. So what we've done with the dashed lines that you see here is everywhere that you see a dashed line, that's where I'm indicating, okay, right here along this path is where they happen to be in phase from that. So at this point, for example, right here, then both the top wave and the bottom wave, the lines have actually intersected with each other. And the lines that were representing the peaks have intersected with each other. And so that's going to indicate where we've got constructive interference. Okay, now that you've got that, you should be able to very easily label where am I going to get bright and where am I going to get dark. So go ahead and do that right quick. Well, remember, constructive interference, if they're in phase, is going to give me a bright spot. So I've got a bright spot here, I've got a bright spot in the middle, and a bright spot down here. The one in the middle is maybe the easiest to see. You can see that that's where those lines are intersecting right there as we look at it here. And you may say, well, okay, well, what about the part in between? Well, if it's not bright, it's going to be dark. So we'll label those with dark. And that's going to be something that we're going to be using quite a bit here. Sometimes we can't actually plot the position of the dark fringes. That's what these little lines are going to be called. We can't plot the position of those destructive interference points. Instead, we know that they occur halfway in between the places where I have the bright constructive interference, where they're actually directly in phase. All right, so now if we're going to color in what that looks like, and I'm going to do this kind of off, let's do it in red. So let's say I had a red laser then I'll get that central bright point in the middle. And then we would have this one over here, and maybe they're going to be fairly big. And then I would have this over here. Now I also have interference extending out this way and this way. Because if you think about it, those waves are still expanding out. And so even further on out, I'm going to get places where I have this constructive interference. So this pattern, this bright and dark oscillating pattern, extends outward all the way out through here. Now, most of the energy, as we talked about last time, is going to be going through the center. That makes sense, right? So most of the energy is going to be going through the center, so it's going to be the brightest. Conservation of energy, I've got a limited amount of energy. The total energy on all of those little bright spots has to equal the total energy in the 2 lasers from here. So that would mean that the amount of energy in each one of these bright spots as we move out has to get less and less and less. Okay, so this pattern that you see here is called an interference pattern, because they're interfering with each other. And by tradition, we call the lines themselves, the bright spots, are called fringes. And you can think about that as, because you've got fringes on a curtain or some sort of cloth dangling down like that. It's kind of what it looks like. We talk each band, we call a fringe order. So this central one is the 0th order fringe. It's the central maximum. This is a first order fringe. This is also a first order fringe because it's the first one on either side, and they will have the same brightness. They will have the same intensity. If I have another one over here then, which may be off my screen, that would be the second order and third order, and so on and so on and so on. And traditionally what we'll use is an integer to indicate that. So we would say that this would be the m equals 0 fringe, this would be the m equals 1, m equals 2, and then I might say that this is m equals minus 1, m equals minus 2 if I want to indicate which side I'm on. Realistically, you're going to get the same, it's the same distance, just doesn't matter which way you're going. Okay, so this key right here, this is our interference pattern. And it's very simple to think about. It's simply where my two waves are interfering. Do want to make one comment though. Take a look over here. I've been talking about having two lasers. I don't actually have two lasers in this particular case, do I? I have a single laser that's firing upon these two slits. But remember, because each one of these slits has its own wave emitters as it comes through, it acts like I have two lasers there. I could do the exact same thing if I had two physical lasers shining and interfering with each other. The problem that I have is I've got to get these things lined up to be exactly aligned with each other. They also have to have exactly the same wavelength for everything that we're talking about here. And there's always going to be some variation in what we're looking at. So usually if I want to get this kind of pattern, I want to have a single light source that's passing through two apertures, through two slits. And then I'll get these kind of patterns that we're looking at. Okay. All right, let's move on to the next one. We'll get rid of this. Maybe we'll get rid of this. There we go. Okay. So I've zoomed in on our pattern here that we've been looking at. So this is what we had before. And here, this line that I'm drawing, I'm going to use that to represent the direction these wave fronts are propagating. So this is perpendicular to my wave fronts. So this would be the same picture that I had before, but instead of having my wave fronts moving this way, I'm just going to say, okay, I'm tired of drawing all those curved lines. So I'm going to draw that path perpendicular to them. Okay. So that path right there is perpendicular to these wavefronts, but it shows the direction in which the wavefronts are moving. This, by the way, is the origin of the light ray that maybe you've heard about before. But really, it's nothing more than a notational convenience. It just, because I'm lazy, I don't want to draw all these lines that are here. So instead, we'll say, okay, this path that you see right here, then, that's the path of all of those waves moving this way. Whereas this one is going to be the path of all of these waves. Get my mouse to release there. There we go. All right. So let's get rid of this. So furthermore, we've zoomed in on this area right here so that you can see a little bit better what's going on, because we're going to need to use some geometry to figure out what's happening here. So D is the distance between the slits, between the apertures. All right. Now, these two waves are the waves that are being emitted from the, we'll call it the center here. Again, though, remember that I've got multiple wavefronts coming out here, but this is one wave and this is the other wave. So we look at microtest 2 then. If the path length difference is exactly one wavelength, what type of fringe will appear where they interfere? And we did this last time. Let's go ahead and draw that. Suppose we'll draw this down here to the side. We talked about how if I have two electromagnetic waves, so here's my E field, but I'm going to have one that's going to start out back here. So it's going to travel a slightly longer path to reach this. So this will be E2 and this will be E1. That's the best I can do with that. So you see that if I am exactly one wavelength away, so if my path length is exactly one wavelength longer, then they will be in phase. So if they're exactly one wavelength, then I'm going to get a bright fringe. If they're half a wavelength, then by the time they meet together, then they're going to be out of phase, and they're going to cancel each other out. Okay, so we want to come up with a mathematical expression for the difference in the path lengths. Now, here's the hint that we give you. This length, let me do this in red so that we can see it. This length and this length are the same. And this ray goes all the way to my screen. Okay, so you may say, oh, well, wait a minute, how can these two ever be the same if they're parallel to each other? Well, remember the small angle approximation. If that angle is very, very small, and it's a long way away, then I can consider them to be parallel way back here from this. But the key thing we want to recognize is that everything to the right of the dashed line that you see here, that dashed line right there, that's all the same length. So what can you say about x? X is this distance here, and it goes from here to here. If I have a bright fringe, what can I say about x? Well, x must be equal to one wavelength, right? So x must equal lambda in order to get a bright fringe. That's the key condition. In order to get a bright fringe, then I'm going to have x equal to my lambda there. All right, so now we can use trigonometry then. I'll get a bright fringe whenever x is equal to lambda. So x, though, is going to equal, let's say that, I think we defined this to be, yeah, you can barely see it right there, but this is my angle theta right here. If I blow this up even more, that's theta, okay? So how would I write that in terms of trigonometry? Well, x is going to be the opposite. Notice that d, lowercase d here, this is the hypotenuse of my triangle. Let's draw that and make sure that everybody sees that. That's the hypotenuse of my triangle. That's x. This is theta. So is that going to be sine, cosine, or tangent? It's going to be a sine. So this is going to be, let's go ahead and write it out from full first. The sine of theta is going to be the opposite over the hypotenuse, so x over d. And so that means x is going to equal to d sine theta. Now that's true for anything, right? X, it doesn't matter whether I'm one wavelength in phase or not. However, if I am actually going to have bright fringes, I need that distance x to equal one wavelength. So let's scroll up here. So we want to find the mth bright fringe. And by that we mean, remember, our zero order fringe is going to be in the middle, then our first order, second order, third order. And each one of those times I have to have a distance equal to a multiple of the wavelength. Let's do it for the first fringe to start off with. Well, that one we said, okay, I have x equals d sine theta, but for the first fringe, that's equal to exactly one wavelength. And so that's going to be m is equal to d sine theta. So that gives me the location of the first m lambda, sorry. If m equals 1, that gives me the location of the first fringe. If m equals 2, now they're 2 lambda apart. They're 2 wavelengths apart. They're still going to be in phase, though. Make sure that makes sense to you. If they're 1 wavelength apart, let me draw our picture again. So here's one of our waves. That's kind of our comparison line. If I'm 2 wavelengths out, 1, 2. You see that I'm still going to get constructive interference. So I'm still going to get bright fringes where they interfere with each other. So this then is my general, where it's plus or minus 1, plus or minus 2, plus or minus 3, and so on and so on. Okay. Now, What about the dark fringes? Well, the dark fringes occur when it's half a wavelength. So the way that I can think about that then is it's going to be m plus a half times lambda is going to equal d sine theta. And of course, if m is 0 up here, that's going to be my central bright fringe. If m is 0 here, well, then that's going to be I'm half a wavelength out. And so now they're going to destructively interfere. Let's make sure that we can see that. So here's E. There's my comparison wavelength. Here's my line here. And that would be a whole wavelength, but if I stop right here, let's go ahead and sketch it now that we have our distance. You see that now they are going to be out of phase. They're going to be 180 degrees out of phase. Okay, so you see that when we put all of these patterns together, we're going to get something that kind of looks like what we see here. The central bright fringe, and we're showing this here on this side. So this would be our central bright fringe. And then the fringes get dimmer and dimmer and dimmer as we move outward in either direction. Now, on the right here, we've got another graph that we're going to find very useful through here. This is showing the intensity. And yeah, in this case, it's going to be the intensity. It's not going to be the current or the moment of inertia and everything else we've got. But versus some distance, and maybe we'll call that x. So this peak then is showing us that this fringe is bright because it's got the highest intensity. So this would be our m equals 0, our central fringe, or central maximum. This then might be m equals -1, m equals -2, m equals -3, and so on. And then, of course, on the other side, we've got m equals 1, m equals 2, and m equals 3. And that extends on to infinity. And like I said, it actually does extend on infinity. I mean, this theoretically extends all the way to the moon, but because of conservation of energy, there's very, very, very little light, very little energy by the time I get out very many orders away from that. And so it's beyond anything that you would ever hope to detect, and it can get lost in any kind of background information that we have. Okay, so now here's a little puzzle for you. Suppose I don't just have 2 fringes, but suppose I have more than 2. So for example, if I have 3 fringes, how is our expression going to change? So we want to come up with a mathematical expression for that. And the way to do that, the way to approach it is, okay, I want to come up with an expression that holds if I have 2 fringes, because we already know what that looks like. And we're just going to sketch that out to the side here. But remember, that's going to be m plus 1/2 lambda is d sine theta, right? Because then when m is 0, I'll get half a wavelength. When m is 1, I'll get 3/2 of a wavelength, and so on and so on and so on. So whatever we get when we have n slits needs to also satisfy that when n equals 2. So pause the video and think about it. It's just a little bit of a challenge, a little bit of a puzzle. See if you can figure it out. Challenge yourself. Okay, so one possibility might be to say, and I'm going to use k instead of m just so that we don't get confused between which is which. If I have k over n lambda equals d sine theta. That kind of works if we think about it. So if I have k equals, well, if k equals 0, that doesn't work, does it? Because that's going to give us a bright fringe, right? So let's start with k equals 1. And again, we're going to test it for n equals 2. If k equals 1, then I get 1/2 lambda. That works. But if k equals 2, that doesn't work, does it? How about 3? Okay, that works. 4, because 3 then would be 3 divided by 2, 3/2. And 4 is not going to work, but then 5 is going to work, and so on and so on. And you say, okay, well, cool, I'll just do all of the odd numbers until we start to decide, okay, well, what if I have 4 fringes? What if I have 3 fringes? So if n equals 4, right, then I should get it at 1/2, at 1/4, 1/2, and 3/2. Well, okay, 0 obviously still is not going to work. 1 works. 2 now, the 2 is actually, 2 over 4 is going to be 1/2. That's going to be a dark fringe. That's what we want. 3 still works. That's 3/4. 4, though, does not work. Do you see that? Because now I've got 4 over 4, and that should be a bright fringe. And hopefully you can see the pattern. What this is going to happen is that, yes, this works, but if this assumes that k over n is not a whole number. So that would be our formal solution to the puzzle, would be this is going to be the equation for the dark fringes, and it's going to be k is an integer, 1, 2, 3, 4, 5, and of course negative signs too. But 1, 2, 3, 4, 5, but with the exception that k over n is not a whole number, and that'll apply to everything. Now, some students get a little bit confused because my bright fringes, of course, are going to be in the same spot. So what you see here, all of my bright fringes have to be exactly where they were before. But now I'm saying I've got dark fringes in between. Well, how do you have a dark fringe without also having a light fringe? And in fact, we do. They're called secondary maxima. They're much, much fainter than the primary. And so what happens then is, let's say that this was my original. Well, let's say that my original was quite wide, like you see here on this side. Then what happens is, since I'm getting more dark fringes and then some very, very faint light fringes in between, then the end result is that my bright fringes actually get narrower, my primary bright fringes. These still look mostly dark, but if you look very carefully, you can see that it gets a little bit brighter here, then dark, then a little bit brighter here, then a lot brighter, and then so on and so on. So what is happening then to the energy? Remember, it's conservation of energy. I've got less energy being spread out over this big distance here. The energy is going to be the same, but it's over a smaller area, which means the intensity is going to go up. Because remember, intensity is going to be our power, the amount of energy per time, divided by that area from that. So that means, you can think of it this way, I'm taking the same amount of light and I'm concentrating it in a smaller area. And so these things are going to get brighter as a result. And the more fringes, the more slits I have, the more apertures I have, the thinner these lines are going to be, and therefore the brighter they're going to be. You have probably seen, you probably called them rainbow glasses, but you put them on, you see rainbows everywhere from those. Those are actually something called a diffraction grating. And a diffraction grating is often a piece of glass or plastic in which we've engraved slits in them. We don't actually have to cut a hole all the way through it, because the flat plane, remember, is not going to diffract anything. It's just going to let everything go straight on through. But I will put thousands of lines right next to each other, thousands of tiny little slits. So in the space of, where here we might have had one slit, if I've got my two slits this far apart, now I've got 1,000 slits in that same amount of space. That means that the diffraction lines, these interference fringes that you're going to get, are going to be very, very thin. And then they'll, of course, be very, very bright. So a diffraction grating is one of the better ways that you can see this interference pattern. It's actually easier than even just taking, okay, I've got two pieces of cardboard, I'm going to put them next to each other. Yeah, you'll get fringes from that. You absolutely will. But they're going to be very wide. They're not going to be terribly bright. And it's going to be hard to see. By using one of these diffraction gratings, then we can get it a nice, sharp, and bright diffraction pattern that we can see. Now, if we look down here, and there's a discussion here, that's what we're talking about with diffraction gratings. You may say, well, why do we see rainbows instead of individual bright images? So if my light, is shining through it, white light, for example, why am I getting rainbows? Well, remember that white has all of the different colors in it. So this is going to be important for us, but white has all the different colors of the rainbow in it. So for the visible wavelengths, that's anywhere from 400 nanometers to 650 nanometers or so. But each one of those has a different wavelength. Each color has a different wavelength. And so if we go back to our expression for our bright fringes, because that's what we're mostly interested in looking at, it's going to depend upon the wavelength. So that means that the angle is going to be different for each of the different colors. So let's solve for the angle here. I get m lambda over d is going to equal sine theta. So you see that as lambda gets smaller, which corresponds to blue light, we're going to learn, then sine theta also has to get smaller. And that tells me that that angle there has to change as well. So what happens then is that since the angle is changing, blue and red will be in different positions. And so that white light is getting split, and that's what's causing your rainbow. All right, so let's see if we can do a problem with this then. Go ahead and delete this part, and then we'll erase what we've got here on the sides. And this is very similar to what maybe you would do in a lab experiment. The way a CD works, a CD-ROM, CD, audio CD, anything like that, is it burns. So I've got basically a reflection. I've got a reflective surface here, a mirror, say, and then on top, I've got some plastic that I'm burning these grooves into. And those bits, those bumps, that's what encodes the data so that you can see that. Well, those things are very, very, very close together. Now, remember that if I have a light ray coming in, if it hits the mirror part, it's not going to be affected. It's just going to come straight back. But it can't make it through these grooves. So this acts like a diffraction grating. So this effectively then becomes a slit. And in fact, it's multiple slits, which is why we're going to get a nice tight diffraction pattern. If you've ever looked at a CD or a DVD, you can often see that rainbow reflected in there. That's because the light's being diffracted different amounts. So the different colors are being sent off at different angles, and so that you're able to split that. Well, we can use this property to figure out what is the spacing between this. We can literally measure things on the order of a micron, but 1/1,000,000th of a meter using this technique. Interference is a very powerful technique for doing this. Okay, so let's take an example. So let's say that we've got a red laser pointer, and it's about 650 nanometers-ish. It's not exactly that, but you'll find it printed on the laser. And we're going to reflect those fringes onto a screen that's 40 centimeters away. So this, we'll call this capital D, and we're going to say that that's going to be 40 centimeters away, or 0.40 meters. Okay, we measure the distance between the central, here's our central, this is m equals 0, and this is m equals 1. So this is our first bright point here. Here's our central one, here's a bright one. We measure that distance, and we'll call that A, to be 16 centimeters apart, so 0.16 meters. All right, we want to know what is this D, the spacing in between those bumps, those grooves that are making the diffraction pattern that we see. All right, this would be a really worthwhile exercise for you to pause the video and see if you can work it out in your book, because it's basically, you've got everything that you know. It's going to be exactly the same kind of thing that we've done. Go back and look through the earlier part of this section, and it'll give you the zoom in part on the geometry of what's going here, and you'll be able to figure it out. So pause the video, see if you can get it, and then we'll come back and we'll work through the problem. Okay, you got it? Let's see how you did. So for our design, we're going to assume that the spacing on the CD, so that's between those bumps, those grooves on the CD, is going to equal D. That's going to be our slit width. We're also going to assume that D is much less than big D, so that I can use this small angle approximation. And that's pretty reasonable, considering these are going to be the order of a micron, right? And then we're going to use our diffraction expression to get D. All right, so let's define our quantities. So D is going to be our distance, and so that's going to be 0.40 meters. Let's be really clear, that's the distance to the screen, because we've got a number of different distances going on here. We defined A, 0.16 meters, and that's going to be the distance to the m equals 1 bright fringe. And I'm setting this to be my 0 for distance, and there's no reason not to, right? I can set my m equals 0. I can set my 0 anywhere I want, so I'm going to set the location of my bright fringe, my central bright fringe here, to be 0. So A is now that distance through here. Okay. All right, let me zoom up a little bit so that we can see what's going on. There we go. Okay, and we want to find D in meters, and that's going to be the distance between the grooves, which is also the slit width. And then the last thing we know is that our wavelength is going to be 640 nanometers. So I'm going to write that in meters since everything else is in meters. So this is going to be the wavelength of our laser. Okay. So now all we need is our equations. And of course, the important equation, most important equation, is going to be our diffraction relationship. And so we know that m sine theta, m lambda is going to equal d sine theta. D is what I'm solving for. So on your next page, you've got your step 5 where you can work it out, but we're going to put it over off to the side here so that we can do this. Now, m in this case, we've got a new symbol here. M is 1 because we want the first order fringe. The other thing that we've added, though, is we've added one new symbol, and that's going to be theta. So theta is the angle for what's called the path difference. So that means the problem is now telling us, okay, I've got everything I need except I need theta. So I need some sort of expression for theta. And this is, remember, is how you solve all problems. You start off with your most important equation here, and maybe you've got everything you need, and you plug it in and you're done. But oftentimes the problem will say, hey, you need one more thing for us. So we need that theta. So let's go ahead and magnify our drawing like we did before. So here's theta, which is what I want. This is going to be my slit width, and we called this x, but we want this to be equal to 1 wavelength here. Now you're like, but wait a minute, I don't know D, so I can't do that. However, if you look at the diagram here, this angle, theta, is also going to be equal to that angle up there. And we could walk through all of our arguments here so that you can see that, but this angle theta must be the same as that. And if you want to convince yourself of that, let's say that this is a right angle as well. So this angle is going to be 90 minus theta, right? And if this is a right angle, then this must be 90 minus 90 minus theta. In other words, theta. Okay, so walk through the geometry, make sure that you understand. Here's a right angle here, here's my other right angle, and that's how I can figure out that. That's going to be real common. We're going to do that pretty much all the time. So now I know that this is capital D, and I know that my spacing between the two, which remember was measured here, those distances are going to be the same on my big triangle. This is the little triangle. This is my big triangle here. I don't want to draw it in 2 different scales. So now I know that theta must be equal to the tangent of theta must be equal to my opposite over my adjacent. And so that's going to be A over capital D. I'm going to get rid of these so that we're not too confused with that. There we go. Okay, so hopefully see, I'm going to bring this over to here, and that's A, because those have got to be the same. Here's my big triangle, not my little bitty triangle that I'm drawing here. I just use that to make the association between these two thetas. Okay, so there's my second one, and work through that, but we're going to do that pretty much all the time. So that's worth having in your flip book for this. This is how we're going to get theta most of the time. So theta then is simply going to be the inverse tangent of A over D. All right, so let's do that here. Now we've got everything that we need. We didn't add any new expressions. So I'm going to work out first. I'm going to go ahead and get a number for my theta. Oops, that should be a capital D. And so theta is going to equal the inverse tangent of A over D. And we decided that was 0.16 meters divided by 0.40 meters. And punch that into your calculator, and that will give you an expression. So let's go ahead and take our calculator and let's do it. Let's work out the number. 0.16 divided by 0.4. And I get 0.4. That makes sense. So, and then I'm going to take the inverse tangent of 0.4. Oops, I have to do that first here. And I get that theta is 21.8 degrees. Okay, so now I'm ready to go back to my other expression. M is 1, so I've got lambda is equal to d sine theta. And so lambda over sine theta must equal d. So that's 650 times 10 to the minus 9 meters divided by sine of 21.8 degrees. And so 650 times 10 to the minus 9 divided by sine of 21.8. And I get that the split spacing is 1.75 times 10 to the minus 6 meters. In other words, it's 1.75 microns, which is pretty reasonable. Okay. So make sure you follow that. Make sure, particularly when we're trying to relate how that theta is actually equal to how it corresponds to our big triangle, between the big triangle and the little triangle. And obviously you could say, oh, well, I'll just accept that because Dr. K said so. But it's worth you going through the geometry so that you can see those angles have to be the same. Once I have that angle, then, if this is D and this is A, if you agree that that's going to be that angle right there, then it's pretty easy to see that that then has to be the tangent. Okay, so what you've seen today is that we can use interference to measure very, very tiny differences in distance from that. And that's a hugely valuable technique because in many cases we want to measure something really, really small, but I can't just take a ruler and stick it down there and see what that's going to be. There are lots of applications to this. We can use interference to measure the distance between atoms. We can use it to measure gravity waves that are coming through from space that are causing very tiny changes in space and time from that. All of these things are available because we can use this diffraction pattern from that. So learning how these things interfere with each other and the pattern that they produce is a very important scientific measuring tool that you're going to see quite a bit throughout your career. All right, we'll see you next time.